I'm sure by now I've convinced everybody to love graphs. I'm sure that's a done deal, which means, of course, that we're all excited to write some algorithms to find properties of graphs, to do things like find paths and test connectivity, and to benefit from modeling a problem as a graph by being able to solve complicated global questions about a structure by modeling it using local properties like pairwise relationships. But of course, we can't do that until we have some way of representing our graph inside the computer, and so we have to talk about graph representations. And I promise this will be a lecture on the shorter side. There's not really any theorems to prove. We just have to discuss a few options for how to represent things and reason a little bit about the running time. So it's a good old-fashioned data structure lecture. So the task is, let's create a data structure to represent a graph. And remember that formally, so in a mathematical sense, a graph is a pair of two different sets, V and E, the vertex set and the edge set. And so we can think here, I've drawn this, we could actually put set brackets around these two things, and there we have it. There's our vertex set V and our edge set E. And so I guess one natural try, if we want to design a data structure, would be just to represent the vertex set as a set and the edge set as a set. So use some sequence type or something to store the list of vertices and the list of edges. We obviously have that. And we know from earlier in the course that it is, I think, a sort of healthy first try. When you need to design a new data structure to represent a collection of things, just start by storing them all in an array. Just use some basic sequence and see where that takes you. And that actually is a valid representation. So the most obvious way of storing a graph, I think, is to store the vertex and edge sets directly. Typically, we call this thing an edge list, although I don't think there's some canonical name for it. It's used often enough that people tend to call it an edge list, but it can be called all sorts of things. There are plenty of cases where this is a really useful representation, and the reason I guess that we say edge list versus vertex list or something is that typically storing a list of vertices isn't the hardest thing in the world. It's storing this collection of unordered pairs, edges, and finding some way of searching that. So typically the edges take precedence, and we call the thing an edge list. We could use edge lists for directed graphs or undirected graphs because it's just a matter of interpretation. So if I store this edge list and I indicate or I understand that the edges are undirected, well, then I can interpret it to mean that it refers to this undirected graph. And if I store this edge list and we choose to interpret its elements as ordered pairs, well, then it corresponds to this directed graph. And because this is basically just mapping directly the mathematical definition of vertices and edges into a list structure, it's pretty clear that we can store a graph this way, and then we can store it pretty efficiently. That is, we just have one entry in my list for each vertex and one entry in my list for each edge. And the edges have a constant size, that is, each of them contains two vertices, and 2 is a constant. So the total space complexity is just the size of V plus the size of E. That's no big deal. And edge lists are nice because they're very basic and simple, essentially, which is, if I were to hand you an edge list and I say, I've encoded an edge list, or here's a text file containing the edge list for a graph, it's very easy to explain how that works. There's no extra structure to explain, and so edge lists tend to be very useful for if you have to provide information about a graph between two different programs. So for example, when the automation that makes these slides draws graphs, the graphs are actually specified by means of Python code into a format that uses an edge list for drawing, because it's an easy way of transporting information about a graph between two different programs. In this case, the Python code that generates the graph layout and the LaTeX compiler that generates the slides. And so edge lists are great, and you will likely find if you work with graphs and algorithms that one day you will have to use edge lists for something. There are programs out there that can take edge lists and automatically draw the graph. They can find some way of laying the graph out that looks reasonably readable, and generally they work with edge lists. So edge lists are great, even though we're basically never going to use them. So for our algorithms, we're going to find that we need a more structured representation. But we shouldn't sell them short. Edge lists are great, and they are useful for specific cases like that they are convenient and very easy to understand. And so if you have two different programs that want to work with graphs, they're a very easy and safe format for common understanding of graphs between programs. The problem is we often find ourselves wanting to ask questions about graphs that have to do with maybe vertex-centric things or edge-centric things that edge lists can't really help us with. So, for example, are vertices U and V adjacent? Okay, so I could ask, for example, is there an edge from E to C? Well, I could search my edge list somehow, but I would need to define some search procedure for that. That wouldn't be too difficult. If I store my edge list in a binary search tree or something, a red-black tree, for example, and I use as the comparison logic, I first compare the source and then the destination, that would be useful for a directed graph. But in an undirected graph, let's go back to the undirected one. If I have to ask the question, is there an edge CD? Well, okay, then what I would have to do is first, depending on how I'm storing this, I might ask, does this edge exist or does this edge exist? They're the same edge, but they could be represented in two different ways. So searching my edge list there could be a little bit cumbersome. But also questions like, what are the neighbors of vertex V? So for example, could you tell me the outbound neighbors of vertex E? Doing that seems to require iterating over the entire list. I have to iterate over the entire list and just print out or output all of the edges I see that begin with an E. If I say stuff like, what are the inbound neighbors of E? Okay, so now I have to look at all the edges that end with an E. That would be G, E, and F, E. Is that it? I think that's everything. So I do this by iterating over my entire edge list, which is sort of cumbersome because I can think that, the maximum number of edges in a graph, which has n vertices, is this. In other words, the size of my edge set is n squared in the worst case, big theta of n squared. And that means if I have to iterate over my edge set to ask basic questions, I might, incur pretty significant performance penalties as a result if I need to ask that question a lot for an algorithm. And it turns out that for what I consider to be the most important algorithms that we're ever going to study in this course, and critical algorithms for graph, which are called graph traversal algorithms, we often need to ask questions constantly along the lines of, here's a vertex, tell me its neighbors. Tell me the neighbors quickly, please. And an edge list just can't help us with that. So we need more structure to be able to represent graphs in a format that's convenient and efficient for some of the algorithms we need to use, which often want to ask questions about the neighbors of a vertex, listing the neighbors of a vertex, and very quickly retrieving information about are two vertices adjacent. So if I want to ask, is C adjacent to D, or is there an edge from C to D, I can do that, but only by searching my edge list. And if I'm careful, that search might only require log n time or something, but I want to see if I can bring that down, because there are algorithms that require tons and tons of queries of this form. So our next structure is called an adjacency list. And it's a more structured format where I have a list of all the vertices mapped to lists of their neighbors, basically. And you can see here with this undirected graph, if I let's look at vertex D. Notice how in the table or in this list, so I choose to draw it as a table, but you can see what it really is sort of a dictionary that maps vertices to lists of neighbors. In this dictionary, if I look at vertex D, notice how it lists B, C, and F. Those are the neighbors of vertex D. Which means if I want to ask the question, what are the neighbors of D, well then I just go to the table and look at the list. That's easy. And iterating over the neighbors can be done in time proportional to the degree of the vertex. So if I want to iterate over all the neighbors of vertex V, for some vertex V, that can be done in this amount of time. Big theta of the degree of V. That is to say, basically constant time per neighbor, which is pretty good. If I want to ask the question, is there an edge between C and D, I do still have to do a search, but at least now I can do the search more locally. So I can say, I want to know if D is a neighbor of C. Well, let's just go into the list for vertex C and search it. Okay, well, the search could take a long time, and we know that in the worst case, the number of neighbors could be up to n minus 1. But that means that I could now be searching in maybe linear time, or if I store my list of neighbors in sorted order, I could get it down to log of the degree of the vertex in terms of its time complexity. So in an undirected graph, because edges are symmetric, that is to say, if there's an edge between C and D, then C is a neighbor of D and D is a neighbor of C, and they're both considered equals, then the adjacency list entry for each vertex just lists all the neighbors. So C's neighbors are A, D, and E. D's neighbors are B, C, and F. In a directed graph, where there is a sense of order to edges, a direction to edges, then I actually might want to have two adjacency lists. So typically in a directed graph, if I just say create an adjacency list, typically what I'm talking about is a list of outbound neighbors. Now if I want to, I could create a list of inbound neighbors, that's fine, but typically if I say nothing else and I talk about adjacency lists on directed graphs, I'm talking about outbound neighbors. And the idea there is, let's look at vertex D again. The table here lists the outbound neighbors of vertex D. So you can see it's we've got B, because I can go from D to B. We've got C, because I can follow this edge here, and we've got F. If I look at the outbound neighbors of F, I only see E because F has plenty of inbound neighbors, but the only place I can go from F is to E via this edge here. Now, the reason why typically an adjacency list lists outbound neighbors is, as we're going to see in the coming lectures, we often find ourselves writing algorithms that adopt the sort of convention that at any given point in the algorithm we are standing on a particular vertex and we want to know where can I go from here. So if you're standing at vertex E, and I find that the best sort of real world analogy for graphs for a lot of these things is to think of this as being a set of roads that go between cities, or like one-way rail links or flights you can take from city G to city E or something like that. So you're in city E. And you're asking the question, you're standing at the airport and you're like, where am I allowed to go from here? Well, there's a flight coming in from city F. Well, you don't care. You want to know where you can go from city E. You care about the outbound neighbors. So when you're standing on a particular vertex, quite often you find that what you care about isn't who can arrive at this vertex from somewhere else. It is, where can I go from here? And that is the relationship of being an outbound neighbor. So from vertex E, I can travel to city C or city F. There might be some inbound neighbors, but this adjacency list doesn't tell me what they are, at least not easily. If I want to know the inbound neighbors and all I have is this adjacency list, I have to iterate over all of the other vertices. So if I want to know the inbound neighbors of E, I iterate over every other vertex and I just pick out every vertex that contains an E in its list. That is not efficient. So if I need that, then I would create maybe a second adjacency list only of inbound neighbors. So we'll see that we rarely need to do this, pretty much always. So we're going to use adjacency lists far more often than everything else. And I write tons of code involving graphs for both the purposes of teaching this course and for lots of other things. And I would say that I probably use adjacency lists for more than 99% of my uses of graphs. And the remainder, I probably use a lot of edge lists for things like transmitting graphs between different programs because it's a convenient format to use for that. And there's a third representation that's optimized for a specific case that I use very rarely, but when I need it, it's really useful. But generally, we're going to find that adjacency lists are our standard graph structure. So even though we can represent inbound neighbors, we'll discover that if we have a directed graph, we care enough about directions that we typically only ever care about outbound neighbors. Rarely is it the case we need inbound neighbors, although there are situations where we make a new graph where we reverse the direction of edges for the sake of checking some property. And I'll come back to that in a few minutes. So it's often the case in practice, like we tend to draw these graphs where vertices can be anything and they can have any name we want because vertices are abstract objects, and in a theoretical sense, when I draw a graph on paper, the vertex can be anything I want. But it tends to be inside of a computer. It's very common to represent graphs by numbering the vertices, and you number them starting at 0. And the reason why this is helpful is it means instead of actually having to use some sort of dictionary to represent your adjacency list, which has overhead because of course the dictionary requires extra time for lookups, if I arrange it so that all of my vertices have consecutive numbers, then what I can do for my adjacency list is just use an ordinary array. If I want to know the neighbors of vertex 5, I just go to index 5 of my array. It's like an array of lists. It isn't very different from the overarching structure of like a hash table with chaining, although it wouldn't be a hash table. It would just be an ordinary table that has a list attached to every index. And I find that I do this as well. So even if you give me a graph that has arbitrary names attached to vertices, what I will often do, if you hand me a graph like this where vertices have some arbitrary names, I will assign a numbering to the vertices, any numbering I want. So where they're listed A through G, I would probably number them sequentially, like this is V0, this is V1. But even if the vertices were numbered sporadically, like one of them is called A and the next one's called J or something, you can always, in your code, assign a numbering to the vertices of whatever variety you choose, so you can number them sequentially, and then just separately maintain a mapping of your numbering back to the vertices' original name. So once you're done your processing, you can convert everything back into the original representation. What that means is that in practice, it's very easy to ensure that you can represent an adjacency list using an ordinary array. And that means once you have that numbering, if you want to know the neighbors of a vertex and you know the vertices number, then what you can do is just go into the array in constant time and grab that list that's attached to it. So the lookups in the adjacency list are, I'm going to assume going forward, can be made constant time by just numbering the vertices. Now, one thing I'll also observe is when you saw this representation of a graph for the first time, you might think by analogy to the way we represent trees, one way to represent a graph is to create a class to refer to a vertex. So in an object-oriented setting, you might create individual objects for each of my vertices, and then each object stores maybe a list of pointers to all the objects it's connected to. So in other words, we represent the graph with some linked data structure, which is based on a sort of node or vertex object that contains pointers to other vertex objects. That's completely valid, and that's a completely valid way to approach a graph algorithm. That is actually an adjacency list. Like deep down, yes, we could store the adjacency list as a single table, one big block of stuff, or we could store it as some distributed structure. That is, this component of the list is attached, I'm going to clear the slide, this component of the list is attached to that object, and this component of the list is attached to this object. That is, even if we have a set of objects, each of which stores a list of pointers, we actually just have an adjacency list. It's just a different way of representing an adjacency list. I really want to make a big deal about that now, because going forward in this course, because for the sake of slides, it's always easier to represent my adjacency list as a table. Going forward in this course, I am going to constantly be talking about using an adjacency list for everything, and I want it to be absolutely clear that I am including this linked structure where each vertex is an object storing a list of pointers. I consider that to be an adjacency list, not just to be a relative of an adjacency list, but to literally be an adjacency list itself. It's just one that's stored a different way than this table is. So keep that in mind. So if I use an adjacency list, then we can actually observe that it still requires big theta of v plus e space complexity. Because if we try and add up how much space everything takes, well, okay, so if I use an array to represent the vertices and then have each element of the array be a list, and let's say we use a linked list, so the size needed for the list is equal to the number of elements in it, okay, well that means that the size of the array is going to be the number of vertices. There has to be one entry in the array for each vertex. Okay, how many entries in all of these lists together? Like, let's think about this. So what are the total number of things? If I use a linked list to store each of these neighbors, how many of them are there in total? Well, let's see. There's going to be, for each vertex, the size of the list, so that the size of this list will be the degree of C, of vertex C. And I realize what that means is that the total number of neighbors altogether, among all of the different lists, will be this quantity. It'll just be the total sum of the degree of every vertex. And because of the handshake lemma, I actually know what that is. That's 2 times the size of the edge set. And so that means that the total size of my adjacency list representation will just be big theta of v plus e. It'll be, that 2 times e, of course, the 2 melts away in asymptotic notation. And so what's great about that is that means adjacency lists are just as efficient asymptotically in terms of space complexity as an edge list. And in particular, they're nice and efficient for representing sparse graphs. And this remark doesn't really have the right context yet because we have to see our next structure to understand what this is referring to. But basically what I'm talking about here is that the size of the data structure depends on the number of vertices and it depends directly on the number of edges. So a graph with very few edges will require less space. Whereas in the structure we're going to see next, the structure requires the same amount of space no matter how many edges there are. And that means that when there are very few edges, you might be maybe wasting space. And so that's one of the reasons I use adjacency lists for everything, is that the size scales based on the density of the graph. So sparse graphs with few edges can be stored in relatively small amounts of space. And they provide pretty efficient lookups of neighbors and iterating over the neighbors of each vertex. And for key algorithms like graph traversals that we'll see starting in the next lecture, the ability to retrieve all of the neighbors of a vertex quickly is really critical. So in an undirected graph, each edge is stored twice because, of course, like the edge CD appears as an element of the neighbor list of C and the neighbor list of D. And as we saw a minute ago, that allows us to employ the handshake lemma to figure out how many neighbors appear in the entire table. In a directed graph, though, each edge is actually only stored once because we only store outbound neighbors. So if I consider, let's do V5 and V6 here. So V5 is one of the outbound neighbors of V6. There it is. But notice that if I go look at the list for V5, there is no V6 in there because this is a one-way relationship. I hope that this makes it clear that really, for a directed graph, if you just store the list of outbound neighbors, you're actually using less space because you're not storing each edge twice, you're only storing it once. Although if you were to maintain 2 adjacency lists of both the outbound and the inbound neighbors, then you would effectively be storing something more or less akin to what you do for an undirected graph, where things get stored maybe twice. Or you could say they just in general do get stored twice. Yeah. So overall, that means that for a directed or an undirected graph, you end up with a requirement of just big theta of v plus e complexity, which is pretty good because obviously you need to store every edge and every vertex, and so you can't do much better than that. Like, how would you store that using less space, other than by using some sort of compression scheme? So I think I got a bit ahead of the slides. The list of neighbors can be implemented in a bunch of different ways. For the sake of realizing that space complexity of v plus e perfectly, you could use, for the adjacency list, you could use an array of linked lists, where each of these lists of neighbors is a linked list. That's pretty useful in cases where you need to modify the graph a lot. So if I want the ability to add new edges whenever I want, so if I want to add this edge, for example, then I want to design my adjacency list in a way that allows me to add as many things as I want to any list at any time, and maybe to remove them. In cases where I want to remove elements, then it is much easier to use a linked list because of all the usual reasons that linked lists allow easier modifications. However, it turns out that I mentioned earlier, I almost always use adjacency lists, and I basically never use linked lists. If I'm writing a graph algorithm in a performance critical setting, so occasionally I write graph algorithms in Python using Python lists because, for example, I'm running graph algorithms to generate these slides, and I don't mind if it takes an extra 0.001 seconds. But if I'm writing an adjacency list in a performance critical setting, then I will pretty much always use arrays. I will not use lists for anything. So what I will typically do in that case is I will use an adjacency list that's based on an array-based structure where the list of neighbors has some maximum size and just assume that that will never be exceeded. I could, of course, observe that every vertex has degree at most n-1 and just allocate an array that's way too big to accommodate every possible case. But often what I might do is, if I know that I don't plan to modify my graph, so in cases where the graph will not be modified after creation, what I could do is create the graph, figure out the maximum degree of any vertex, in this case it's 3, and then just make an array that only has 3 neighbor slots for each vertex. Because I could sort of bake in the properties of the graph to the structure of the adjacency list, because in applications where I'm just using the graph and not modifying it, I know that that will never change after I create it. And as usual with linked lists and arrays, in this course we've got this weird love-hate relationship with linked lists. I constantly keep telling you that in practice people just use arrays for everything. All these clever uses we have for linked lists turn out not to be very helpful because linked lists have all of these practical problems like bad cache performance and the extra overhead of traversing a list. So I tell you that, of course, we always use arrays for sequences, and in hash tables we often use open addressing because the chaining has extra overhead. And on the other hand, I turn around and every time I need a proof of some asymptotic property, I say, hey, we'll just use a linked list for this because it gives us constant time insertion in all cases. So I guess I'm just sort of using linked lists. Me and linked lists have a bit of a toxic relationship, I guess. Linked lists are helpful whenever I want to prove some asymptotic result. When it comes time to actually get the job done, I use arrays for everything. And that's the case with adjacency lists as well. So that's something I've got to work on about myself, that I'm taking advantage of linked lists in that way. But that is true. And in practice, you'll find that often when people are using graphs for, let's say, large-scale searches and things like that, if there's any way they can get away with using a fixed array, they probably will do that because it is so much faster. Now, the question is, so we saw a minute ago that it's pretty clear that if I want to iterate through the neighbors of a vertex, that's very easy. I just go to that index of the array and then loop over the contents of that list, however it might be implemented. The other key question I brought up at the beginning was, what if I want to ask questions like, is there an edge between some particular pair of vertices? So I want to make a query of the form, does edge UV exist? Well, in that case, what I pretty much have to do is to look up one of the two vertices. So let's say I want to look up whether there's an edge between vertex 3 and vertex 4. Okay, so I go to the table under vertex 3, and then I search the list of neighbors and decide whether 4 is in there or not. If I use linear search, well then that would take big theta of d time, where d is the degree of my vertex. Fair enough, and that might not be so bad compared to an edge list structure where I may have to search the entire list of edges. That could be an improvement because we can assume that generally speaking, although this isn't really a worst case observation, generally speaking we can assume that the number of edges attached to each vertex probably is relatively small, or that it averages out to something relatively small. But the problem is, of course, maybe every vertex has degree n minus 1, or size of the vertex set minus 1. That means that in the worst case, testing whether a particular edge exists using an adjacency list could be big theta of n. It could be linear in the number of vertices. And, that's too bad. Life's tough sometimes. That's one of the operations that adjacency lists can't do very well. Now, on the other hand, it turns out that this is an example where, yes, this is the worst case, but when we work with graphs, we often have enough information available to know whether that's actually a real risk. So often we work with problems where we can assert in advance, before we write any algorithms, that the maximum degree of any vertex is bounded by some number. There are specific classes of graphs that we might work with constantly. We're going to see this over and over again, where we can assert formally that, let's say, every vertex, so the degree of any vertex is always less than or equal to 5. Or it's less than or equal to 100 or something. And there are classes of graphs where we can assert that. And in that case, as long as the degree of a vertex is bounded by a constant, then big theta of d is a constant. Although it's not the most efficient constant, because searching a list of 100 things is certainly not going to be instant, it isn't actually linear. So unlike a lot of other cases, like generalized linear search, which we can assume or could have worst case running time that's linear, or in earlier examples like sorting algorithms, where we're not allowed to assume that the array is in a convenient ordering and therefore have to assume the worst case could reasonably happen. Because graphs are so structured, there are lots of algorithms that we can write where we know in advance the degree that we expect the vertices of the graph to have. And in particular applications where you're working with graphs, you might know based on the application whether it's realistic for a certain configuration to exist. So suppose you're doing a pathfinding application on a road network. So each vertex in your graph is a city, for example, and edges represent connections between two cities. So what's interesting about this is that this graph has to naturally, because it corresponds to a real network of real things, it has to correspond to something that could actually exist and be drawn on paper, because a map, if you draw a map of cities, that can be drawn on paper. And therefore there are some reasonable assumptions, and one of them is probably that this is not going to be a complete graph. Like that is, it would be very unusual to have a road network that consists of individual separate roads from every city on Earth to every other city directly. That is, usually if you want to get between two cities, you travel through other cities. So I might go, if I want to get from this city down here all the way up to the top, I might travel like this. It would be highly irregular to have a country full of different cities where every city is connected, every pair of cities is connected by its own private road link. That would be sort of ridiculous. And so hopefully you can see that means if you're modeling a specific problem, there are plenty of reasonable assumptions you can make about the density of the graph, and therefore you actually often know well in advance whether this is truly a possibility or not. This is only a theoretical worst case. In my experience, and I think this is reflected if you look at any source on graph algorithms, it would probably concur with this. This is anecdotal, but I think it is something that's very realistic. In my experience, pretty much all the graphs I find myself working with on a day-to-day basis tend to be relatively sparse. The average density of graphs that I work with tends to be a degree which is considerably less than linear, a number of edges which is considerably below n squared for the graph in total asymptotically. And so, although this is a worst case, it doesn't seem to come up that often in practice, and we can often make theoretical guarantees that it won't occur for a particular problem. Now we have one last structure to cover, which is what we saw with adjacency lists is, although I just said all that stuff about worst cases, this is their weakness. If you want to constantly iterate over the neighbors of a vertex, adjacency lists are exactly what you need. If you want to constantly ask questions like, are these two vertices connected to each other directly, then an adjacency list has a certain weakness that can be a particularly bad, result in particularly bad performance if you are working with a dense graph. The longer the list of neighbors, the harder this is going to be. And so we found a way, therefore, to optimize for iterating over the neighbors. What about optimizing for asking the question whether two things are connected? And that brings us to something called an adjacency matrix. So an adjacency matrix is a 0-1 array. It's a two-dimensional array which encodes whether particular edges exist or not. And it's a pairwise relationship, so it is encoding this for all pairs of vertices. And each vertex gets associated with one row and one column of the matrix. As I said earlier, obviously in practice what you'd probably do is number the vertices, and therefore you can use just a regular 2D array to represent this. So if I wanted to ask the question like, is there an edge between V1 and V0, or between B and A? What I do is I look in row B, column A, and if it's a 1, that means the edge exists. If it's a 0, it means the edge doesn't exist. So let's try G and F. Or let's do F and D. Okay, so I look in row F, column D, and there's a 1. So there is an edge from F to D. I want to ask now about F and C. I look in row F, column C. It's a 0. There is no edge from F to C. For our purposes, because it's just hard to read a matrix full of 1s and 0s, what I'll do is this. I'll just draw the 1s and ignore all the 0s. But for our purposes, please keep in mind that the matrix is a 0-1 matrix. We're talking about an applied data structure here, so those empty spaces are just zeros. We're going to see later in the course that we can actually encode more stuff into an adjacency matrix. There are cases later where we want to attach a weight, a numerical value to every edge. And that corresponds to a case like, suppose this is a network of cities and you want to travel from vertex A to vertex F. But if you want to take this flight from vertex A to vertex C, it costs $5. That's a pretty cheap flight. And if you want to take this flight, it costs $100. And if you want to fly from vertex B to vertex D, it's $150. And if you want to fly from vertex C to D, it's $1,000. And we want to solve a problem like I want to get from vertex A to vertex F with the cheapest total cost. Well, then it's good to associate a number with each edge and have an algorithm that takes that into account. We actually find that adjacency matrices are great for that because you can just add that directly. You could say instead of there being a 1 between C and D, we could just have this be 1,000, for example. So we'll actually discover later that adjacency matrices are a great way of encoding even more information into our graph. Okay, so notice how if I look at any particular row of my adjacency matrix, the 1s in that row correspond to the neighbors. Now, what this tells me is that if I want to iterate over the neighbors of vertex D using only my adjacency matrix, I have to go across the entire row. Which means if the graph is sparse and every vertex has very few neighbors, I waste a lot of time iterating over all of those zeros. And so in a sense, this gives me sort of the opposite behavior as the adjacency list. I can look up whether a particular edge exists really quickly in constant time if my vertices are numbered. If I can access a row of the table for a particular vertex in constant time, I can determine whether an edge exists in constant time. That's great. But in exchange, if I want to iterate over all of the neighbors of a vertex, it actually will require linear time. And I can't really get around that. I have to walk through the entire row of the matrix, and that's going to be n things. And so, as I said a minute ago, the slides are finally catching up to what I said. Typically, you number the vertices so that you can access, every vertex is identified by an integer, accessing rows and columns of the table are simple, basic array indexing operations, which are constant time. So if I want to represent a graph with an adjacency matrix, I need n squared space, where n is the number of vertices, or more formally, v of g squared space. The problem with this is that we know already that the maximum size of the edge set is somewhere in the n squared region. So that is, the number of edges is that's not true, it's big O. The number of edges is big O of n squared. So in the worst case, if we have the densest possible graph, a complete graph, the number of edges can be as much as n times n minus 1 over 2. In a sparse graph, the number of edges could be less than n. It could be a constant number for all we know, but in the worst case, it is n squared. So for a graph that's very dense, where the number of edges is somewhere around n squared, an adjacency matrix isn't that big of a deal because we know that all of the other representations are v plus e. And that means that that would be n squared for an adjacency list or an edge list as well on a graph with tons and tons of edges. The problem is on a sparse graph where the number of edges is tiny, I still need n squared space. And so that means that an adjacency matrix can be pretty inefficient for those cases. And I've mentioned that we often work with graphs that have size, billions of vertices. And obviously, if I have a billion vertices, I don't want to even think about that matrix. I don't want to think about a matrix of size 1 billion squared. I don't think I have that kind of memory on hand. And so to get a proper adjacency matrix where you get constant time lookups, you need to have n squared space on hand. And there are values of n, graphs that we work with, that are simply too big for that to be possible. And so adjacency matrices have to be ruled out in those cases. There are, however, plenty of cases where it is possible and where some algorithms are way faster if we use an adjacency matrix. So, as I mentioned before, in cases where the matrix can be indexed in constant time, so where vertices correspond to numbers that we can index directly into the matrix with, then I can test whether edges exist in constant time just by examining a particular element of the matrix. But if I want to iterate over the neighbors of a vertex, it always requires linear time in the number of vertices because I have to iterate over every position, even the ones that aren't my neighbors, unlike an adjacency list that only stores the actual neighbors. If I want to add and remove edges, that's dead easy. All I do is modify one entry of the table. So if, for example, I guess I've swapped back and forth between V0 and the V0, V1, and A and B representation. So suppose I want to add the edge from V0 to V3. Well, I just go to the entry of the table and I plug that in. And I guess I plug it in both places to be symmetric, which I'll get to in a minute. If I want to add an edge between V3 and V4, I just have to say, okay, so then V3, V4, I add a 1 there, and then I symmetrically add a 1 there. Because in an undirected graph, the edge relationship is symmetric. So, and the slides are right on my tail there. Adjacency matrices for undirected graphs are symmetric because the edges themselves are. In other words, if I actually reflect the matrix across the diagonal, I will see that it's completely symmetric, which makes sense because if I want to look up an edge from either direction, I should be able to do so. If I look up the edge ED in row E, I should see the same thing as if I looked it up in row D. And so that means that row D column E has to contain the same thing as row E column D. For a directed graph, typically, I mean, you could encode the opposite if you want to, but in the representation we are going to use for this entire course, row U of the adjacency matrix always contains the outbound neighbors of vertex U. So if I look at row E of this adjacency matrix, it says that my outbound neighbors are C and F, which corresponds to these two edges here. If I want the inbound neighbors, I don't need a separate matrix. I just look at the columns. So if I look at the inbound neighbors of vertex E, that would be this column here, I see that they are F and G. And we notice that indeed, there is an edge from F to E and an edge from G to E. So unlike an adjacency list, if I care about both inbound and outbound neighbors, they're both sort of equal as far as the matrix is concerned. They're just rows versus columns. As I said, I suppose it is a matter of personal taste whether you choose for the row to be the outbound or inbound end. But in this course, whenever I use an adjacency matrix, the row is always the outbound neighbors and the column is always the inbound neighbors. And I may not say that ever again, but that is now universally going to apply to all future lectures in this course. While we're on the subject of these matrices, because I just observed, for example, that we have a symmetric matrix in the case of an undirected graph, and I guess if we have a matrix, we're tempted to do some matrix stuff with it. So I'm going to define something. I'm just going to make a general graph definition here. So this isn't actually a data structure specific point, but it's a good time to observe this because we're at the perfect place to see this in action. So consider some graph G. It's a directed graph. I guess I should have written that because it's clear from context. Consider some directed graph G. We're going to define what's called the transpose graph of G, and it's noted by G transpose, so G to the power of T, I guess. That is the graph that results from reversing the direction of all edges. So you can see here how G contains an edge from D to F. G transpose contains the opposite edge, F to D. The reason I bring this up now is that the adjacency matrix gives us an absolutely obvious way of computing the transpose. I mean, you can compute the transpose of any graph by hand. You can do it using adjacency lists or edge lists if you want to. But in an adjacency matrix, it's just completely easy. All we have to do is transpose the matrix. That's why it's called the transpose graph. Because what we're really doing when we transpose the graph is we are swapping the set of inbound neighbors and outbound neighbors of each vertex. That's what we do when we reverse the direction of each edge. G was previously an inbound neighbor of E. In the transpose, it will be an outbound neighbor. And what I'm really doing there, therefore, is swapping the meaning of a row with the meaning of a column. So if I do that, so you can see here's the original graph, and here's its transpose. All I have to do is to transpose the matrix, to reflect it across the diagonal, and I end up with the transpose graph. And we will see cases in this course where we need the transpose graph. It'll come up occasionally. I mentioned earlier that we don't often care about inbound neighbors. The reason we don't is because often if we do need to think about inbound neighbors, we use the transpose graph as a proxy for that. We don't directly think about them, at least not on paper, not in theory. In an implementation, you might just use inbound neighbors rather than working with the transpose. But we often use the transpose graph as a proxy that allows us to think about inbound neighbors of a vertex, because transposing the graph just swaps the role of inbound and outbound neighbors. So where does that leave us? Well, we've got pretty much three key structures for representing graphs. And I believe when data structures are concerned like this, when there are three essentially equal but having different advantages and disadvantages things, we sort of have to follow a ketchup, mustard, and relish rule. There are three options, and there's one that's the most common, whether you like it or not. There's one that's always in second place. This also could be like Coke, Pepsi, and Royal Crown or something like that. And there's this third one that's sometimes present, but some people have never even heard of it before. And so I think that if we had to think of which one is going to be Pepsi or which one's going to to be Coke, or which one's going to be ketchup and which one's going to be mustard. I think the adjacency list is ketchup. Although I'm not the biggest ketchup fan, if there's going to be condiments available, ketchup is more likely to be found than mustard. The adjacency matrix is the mustard, and then the edge list is relish. And that is, you may not always see relish, but if it's present, then that's nice if you like relish, which I actually sort of do. And edge lists are useful, but they don't tend to be very useful for most graph algorithms. Adjacency lists are great for most graph algorithms because, as we'll see, a lot of graph algorithms are variations on a traversal algorithm that we're going to see in the next lecture. And those tend to be very fast with adjacency lists. Adjacency matrices have a few really important advantages. If I want to add or test the existence of certain edges, that's guaranteed to be constant. However, I need n squared space to do that on a graph with n vertices. If I choose to use an adjacency list and I just represent the list of neighbors with an unsorted linked list, well then, okay, operations like finding all the neighbors, I can get all the neighbors in degree v time. That's pretty good because that's how many neighbors there are. Testing whether an edge exists requires searching the adjacency, the list of neighbors for a particular vertex, which is going to take degree v time as well, which isn't great compared to the adjacency matrix. Adding an edge is constant if I just add to an unsorted list, of course. Deleting it requires finding it first. Now, if I want to do a lot of tests for a particular edge, but I still want the other benefits of an adjacency list, I could try sorting the lists of neighbors if I store them in an array. So I can't use a linked list for this because the search I'm intending to use is binary search. If I do that, then testing whether an edge exists, I can just use binary search, which means I get log of degree v time. Although I should say, although I always talk about this when I teach algorithms, I never actually do this. For whatever reason, I don't think I can't remember the last time I've ever used a sorted adjacency list for anything practical. Because as I said earlier, it tends to be that most graphs one works with are sparse enough that a regular adjacency list is fine. The extra machinery needed for keeping things sorted isn't really worth it. But if we care about the asymptotic nuance of this, we do have the option of sorting the adjacency list. And that does mean that searching is a little bit faster. I should also observe that if we care a lot about doing all of these operations quickly, nothing prevents us from keeping both structures around, or even all three of them. That is, if I want to test whether an edge exists quickly, but I also want to be able to iterate over neighbors quickly, nothing stops me from storing my graph as an adjacency list on the one hand and also storing an adjacency matrix. I could just keep two representations. If I need to modify it, then I have to update both of them, but that's fine. And there are cases where I've done that. So I can think back in recent memory to cases where I have used both an adjacency list and an adjacency matrix for the same algorithm to make both of those two operations as fast as possible. And because it tends to be that a lot of graph algorithms work on graphs that don't require modification, that is, the graph exists at the beginning of the algorithm and it doesn't change at all, creating an adjacency list and a matrix in parallel isn't that big of a deal. It is true that, of course, you incur more space complexity, and, it could be, n squared could be significant if your graph is sparse, but you get this benefit of constant time lookup whether an edge exists. Now, going forward, we're pretty much going to assume pretty much all the time that we use an adjacency list. I'll talk about when adjacency matrices are helpful. In your practice of graph algorithms, you might find either works, and it could be a matter of personal taste. I keep saying adjacency lists are great, but I might be biased. I might just like adjacency lists. I like adjacency matrices too, but I will admit I do like adjacency lists a lot. So you have some choice in the matter, but we have to be aware of the asymptotic trade-offs of that. Okay, I think that's it. I think we now have all we need from the graph theory point of view. We know the terminology of graphs. We understand the properties of graphs. We've also now seen how to represent graphs in a computer, which means we're finally ready to talk about what I consider to be the most important topic of the course, which is graph traversal algorithms. And that's going to carry us through the next two lectures.